Great, thanks, Chris. Next up, we have Vince Fuller and Glenn Wiley talking about LISP DDT.
Trust you. We're going to assign these twin Daryl, because he's also co-author of the document. Right. So I'm Glenn Wiley. I'm a systems architect at VeriSign. I spend most of my time with ComNet and the A&J roots. We've got Vince Fuller from Cisco and Daryl Lewis from Cisco. And these guys are some of the original authors of the LISP drafts, the DDT draft. It's kind of interesting. I was glad Vince put some dates in his bio on the abstract. 1983.
How many people weren't even born in 1983?
So
show of hands.
I was getting paid in '87 to do stuff with computers, but it was nice to see that he beat me there. So we're going to do a little bit of tag team here. We'll talk about what's going on. We'll give you some reminders about what LISP is. If you don't know what it is, it's not the thing you use to automate Emacs. How many of you guys have done development in LISP actually for production? Oh, come on. So I've been paid to code in LISP back in the 80s. They're like 2 people. Then we're going to talk about DDT, and this isn't the pesticide that you used to see in TV in the 50s. And then finally, we'll go over some of the stuff that's going on at VeriSign with respect to LISP and DDT. So, Vince?
Okay, I'm going to handle this part. We're going to do a review of LISP, how it works, things of that sort. And before I start that, I'd actually be curious to know how many people here have seen one of these LISP, intro presentations before? That's not bad. It's what, about 20% maybe? Because it's been a while since we did a roadshow at one of the regional registries before, and so it's going to be a little bit expired, I guess. It's past our sell-by date. Man, my eyes are good enough to read these slides. But anyway, the first question to ask is, why are we doing this? Why did we start doing this? Well, initially, this was work that was kind of spurred by a workshop in 2006 looking at growth of global routing state in the internet. And there was some concern, and we decided to look at solutions. And one of the solutions that came out of that was LISP. That was the IAB Routing Address Workshop in October of 2006. The concept of ID and locator were something that was first developed back in the 60s. There's a Jerry Saltzer paper that is cited by a guy named Noel Chiappa, who was one of the early developers of internet routers in the 80s. And it's a concept that was kind of foreign to people because the Internet Protocol Suite combines both the identifier, what the endpoint is, with how to get there, the routing information for it. And one of the revelations of this paper and this study that was, again, back in the 60s, was that by commingling those things, it makes it kind of hard to scale the routing system and to give some things like mobility, ability to change providers, things like that. By separating those two concepts, by introducing 2 new address spaces effectively, we give the ability to do those things. Turns out that not only is this a good thing for solving the global routing system growth issue, but you can also do some other things. I mean, obviously you get some mobility advantages. You get multi-homing with ingress traffic engineering, which is really hard to do today in a destination-based routing system. The only tools you really have are, prepending and doing other community hacks with your BGP advertisements. You can also build large-scale VPNs. And it turns out you can also do some encapsulation tricks to make it easier to transition to new protocols. I hesitate to say which new protocol since I'm not a big fan. Yeah, some people know what I mean by that. Picture's worth 1,000 words. This picture is kind of the reason why, when we started looking, this is who here has seen this picture before or some variation of it? You're kidding. That's all? I thought this picture was like in every single IETF or NANOG or RIPE or anything presentation about routing. Since people haven't seen it, I'm going to indulge myself with a minute to explain some of the spots on this curve. No? Okay. Well, the thing is, I love this picture because each of the different inflection points on it tell a story. If you look at the beginning, you have kind of a superlinear growth curve. Then there's a little uptick when we started deploying site or addressing, but we couldn't aggregate the routes yet. Then there's a short downward period. It's the only time the global routing system has ever shrunk. That's when CIDR was deployed. Then nice linear growth as CIDR was working, and then things started to go superlinear again when you had the internet bubble achieving its super growth, and also you started seeing deaggregation for things like traffic engineering. Then that flat spot in the curve, who knows what that is? Exactly. That would basically routing system growth stopped for a year during the collapse of the internet bubble, which is, it's profound that you can see that here. Then you start seeing growth again, and then you start seeing very sharp growth as we started seeing the post-bomb explosion. The little tick mark off to the right of the graph there, that's actually an artifact of the data. It's not really a decrease in the growth rate. So that's why. I mean, we want to try to reduce the curve length there. Quick review of some terminology. Again, we're talking about separation of endpoint ID and locators. Endpoint IDs are the things that hosts use. They terminate your TCP connections or your HTTP sessions. They're things that you want to be able to take with you if you pick up and move your site from one provider to another. They are generally more amenable to aggregation within an organization rather than within the topology. In the LISP world, one of the things we do when we separate this function out is we don't propagate endpoint ID information through the routing system. On the other hand, there's routing locators. Those are topologically assigned. Think of that as being provider-assigned address space. They are aggregated opportunistically wherever the topology allows it. And they're subject to change when there's a change in where you are in the network. If you change providers, you get new locators. If you have a mobile handset that moves from Tokyo to Vancouver, it gets a new locator, even though it keeps the same endpoint ID. User data is all LISP encapsulated because since EIDs are not propagated through the routing system, you can't get directly to them just using internet routing. So you need some encapsulation mechanism and a translation at the edge between the endpoint ID and the locator. The network elements that make up the LISP encapsulation, decapsulation, and database systems are the ingress tunnel router. That's the thing that you send, but generally it's in your default path for traffic exiting your LISP site. It will encapsulate the packet. It will take the EIDs, look up destination EIDs, look up the destination locator, and then it will encapsulate the traffic so that it can be routed through the global internet to get to the LISP endpoint at the other end. The egress tunnel router provides the opposite function. It receives the tunneled traffic, the LISP encapsulated traffic. It unwraps it, takes off the locator header, and then delivers it to the end host, which uses the endpoint ID addressing. Typically, those two functions are co-located in the same box, which we term an XTR, since it's an ITR and ETR at the same time. There are two other types of devices that perform this encapsulation and decapsulation on behalf of non-LISP speaking devices. The proxy ingress tunnel router basically sits on your provider network and accepts traffic, does the encapsulation for it. The egress tunnel router is actually something that you can use for transition and to hop over parts of the network that don't speak LISP. Also to get around things like ingress traffic filtering that get in the way of doing LISP-like things. This is the diagram that shows how the basic LISP encapsulation, decapsulation, and then transport through the intermediate network works. On the left-hand side, we have a source that is sending to a destination on the right-hand side. We have a pair of ITRs, ingress tunnel routers, that it's going to use to encapsulate so they can forward through the intervening internet, and then there are a pair of ETRs on the right side that will decapsulate that traffic and deliver it to the end destination. The first step, this is actually common to pretty much any internet transaction, is you look up the host name in the DNS, you get back an IP address. In the LISP world, that IP address is an EID. You then take that, you take your data packet, it's got the EID source, it's then going to forward it to the ITR because, I won't explain why it knows that it should go to the ITR, that's for later in the presentation. But it will send that to the ITR. The ITR will determine through magic that will be explained later how to get to the destination address, which again is a destination EID. It will look in its map cache. It will say, I have this source going to this destination. The destination locator for this destination is this, I can't read address because my eyes aren't good enough, but you can probably read it better than I can. It will then encapsulate, put an outer header using those locator addresses on it, and then send it into the internet. The internet goes to the first provider. Well, the provider knows how to get to the destination that's on another provider network. It forwards it along to the destination locator, which is associated with the ETR at the other end of the path. The ETR will strip off that header, find the inner address, which is the endpoint ID for the destination, and then it will deliver it to the destination right there. Any questions? Pretty standard map and encap. The magic that makes it possible to figure out what EID translates to what locator is the mapping database. The mappings themselves are actually stored in what we consider a distributed database, where each mapping is actually stored by one of these ETRs and then is propagated through a mapping system, which is really a way to index all the mappings. To get the appropriate locator for a particular destination EID, an ITR will send a map request to an ETR, which then will respond with that locator information. How it finds the ETR is where the mapping database or the index comes into play. There were some fairly ambitious constraints placed on how we would build this database. It has to be able to support millions of sites, and subscription time changes in mappings. We're not talking seconds, but we are talking hours to days. The actual transitions at a greater rate than that are handled by other mobility mechanisms. Originally, when we prototyped this, we looked out at what could we take advantage of that was already available on the internet. Well, there are two large database systems on the internet. There's BGP for routing information, and then there's DNS for name to address translation. Initially, we decided to go with the BGP plus GRE plus VRF approach because we could use existing router technology with only minor changes. Conceptually, it's very simple. In practice, it turns out to be kind of painful to operate. The infrastructure that uses the database and manages this database is made up of a number of other devices. A map server that takes information from the ETRs and publishes it in the database. There's a registration mechanism where the ETRs can give that information to the database. And yes, it does have a security authentication mechanism. Then the map resolver, which acts on behalf of the ITR to find the right ETR going through the map server infrastructure. In case it isn't obvious, these terms were chosen deliberately to be similar to the DNS terms, resolver and server, because they perform relatively analogous functions. LISP-ALT then was the original database indexing technology, is an overlay network of tunnels, generally GRE tunnels, with BGP sessions running across them, where the actual EID prefixes are advertised among the participants in the database. Remember how I said EIDs are not advertised on the internet? Well, they're not. They're only advertised on this private ALT overlay network. Again, ALT was a simple concept, turned out to be really painful to work with operationally, and it took, quite a bit of time. It took like an hour to add a new site because you had to go through a fairly painful process of adding GRE tunnels and configuring multiple VRFs. I don't know how many people deal with VRFs, but I find them hopelessly confusing. So that's when we came up with the need to do something better, and that's when DDT was born. This is a diagram that shows how the old LISP control plane with alt works. The reason that we show it here is because there are some things that are similar, in particular the use of the map resolver and the map server, but all that alt stuff is actually replaced by DDT, which Glenn will go over in a few minutes. Again, we have a destination IP address. ITR needs to figure out what ETR to send it to, and so that it can send a map request and get back the appropriate locator. The way it does this is it has a connection to the alt. It takes the destination EID and it just forwards it across the overlay network to a map resolver. Well, actually, no, excuse me, I'm getting ahead of myself. The map resolver is actually statically configured on the ITR so that the ITR doesn't have to know the details of the database. It says, here I have this destination, I want to send a map request, I'll send it to my configured map resolver. Same thing you would do with a caching DNS server that acts as a resolver for your site. The map resolver, in turn, has a connection to this overlay network. It takes that destination EID and it just sends it into the overlay network, which is routing the EID prefixes. It goes across the BGP overlay network, ends up at the ETR, ends up at the destination map server, which knows the ETR, sends it to the ETR. The ETR then sends a response back with the needing mapping entry. The ITR then can go back to the previous slide and put that in its cache and then forward traffic to that destination EID using the locator address. So that brings us to what is DDT and how does it work? And I'm going to turn it back over to Glenn for that.
Thanks, Vince.
Sure.
So DDT creates a hierarchy very similar to DNS. It's statically configured to begin with. You can think of the ideas of, say transferring zone files, that kind of thing. And there's this idea of delegations that you can hand responsibility for some of the prefixes within a prefix you're responsible for down to other servers. Now, originally, they did try and work with DNS actually with the protocol and ran into some problems. Encoding the prefixes was awkward. They had issues with, there's this idea that we need to be able to offer negative replies. So it became painful. The other thing is DNS does a lot of work with labels. It's a lot of what we do on those servers has to do with compression and handling all the stuff that goes with a label. With LISP, you don't need to worry about that. It's all numbers. So a DDT node will have an authoritative prefix, a set of EIDs that it's responsible for, but it doesn't actually keep the EIDs. It's just, say, like a net block. Those EIDs, the extended EID is a tuple comprised of instance ID, the EID prefix and length, and there are a couple of other little bits in there that you'd see in the standards. The idea of the instance ID, that actually lets us create multiple instances of an EID prefix. Say again? For VPNs. Right, as Vince said, for VPNs. So the DDT nodes will accept map requests, they return map referrals, and that'll either tell the requester whether it needs to go to another DDT node or whether it's going to a map server to actually get the final piece of data. Now, if you think of this as DNS, you can think of this as exclusively name server entries, and the A records would end up ultimately just on the map servers. So you wouldn't have any A records in the sense that you're trying to get to that final endpoint actually configured on the DDT nodes. So the DDT node can also be a map server, and there's really, a lot of this is implementation detail, but you could overlap the functionality. Everything that Vince talked about with the map servers could land on a DDT node. There's the idea that it would return the same messages. Ultimately, it ends up returning an acknowledgement that tells the querier when the query is done, and we don't have to iterate through any more DDT nodes. So the resolver, this is more like a recursive resolver in DNS land. It would do the work of actually hitting each of the nodes. And we'll go through a diagram that shows this, makes it a little more clear. Some of the jobs of the resolver are it caches requests from ITRs. Remember, those are the routers sitting on the at the site that's trying to make the queries out, trying to find where to send traffic. It'll query, the resolver queries the DDT hierarchy iteratively. There isn't the idea that the ITRs or routers need to do this. They hand it over to the map resolver, and it takes care of going out and hitting each of the nodes. You can do things like detect loops and delegation errors within the map resolver. And there's also the idea that you're maintaining a cache here, and that helps us get around potential latency. If you had to do this every time you're setting up a session, that could create some work. So there's the idea that we have referral caches and request caches. So positive referrals, like I said, they're pointers to DDT nodes. It can be a node referral, which means go get the next more specific prefix from this node. It could be a referral to a map server, which says go get your final EID from this, the RLOC for this EID from the map server, and it would say that it's answering with the final EID in that type 2. So the negatives are if you have a map server that has a list of prefixes for which no ETRs are registered, you get a type 3 message. The idea is that a map server can be aware of a set of prefixes but might not have anywhere to send them until an ETR registers for them. There's an idea of a delegation hole. There could be part of the prefix that hasn't been successfully delegated out to another DDT node, so we don't have anything more specific to say about it, or not authoritative. That's the idea that somebody has made a mistake. They've asked for a prefix that this node isn't authoritative for. So we'll walk through how you set the system up. Now this is the static configuration. You think of the idea of root hints on a name server or resolver. That's what we do here. We have to identify where the root nodes are for DDT, so it knows where to send its first message. And then each of those DDT nodes would be configured with the delegations. It would take you to node 2, 3, and finally down to the map server. The ETR actually does the registration dynamically. So as an ETR comes online, it would let a DDT node know that it's there. Then we have our packet flow. Now this is actually happening in real time. So the ITR would send a map request to the first DDT node. It says MR there, I think that should be DDT node 1. And the DDT node answers, tells it that it needs to go to DDT node 2. And this iteration proceeds until you get to the final point where you have a map server to go to. Now, this only happens once when you first start the session or when TTLs expire. After that, you end up in a steady state. We'll see that on the next slide. But it's the idea that the MR can now carry a conversation directly with the map server, ultimately getting the information back to the ITR. So that iterative query that we just went through doesn't have to continue to happen. You want to take the implementation status?
Okay, just a brief word on where we are now. We actually have implementations on 2 of the Cisco operating systems, iOS and NXOS. We're also working on one for iOS XR, which runs on the CRS and the ASR 9000. We have a beta network that we've built out of this that we are using DDT on today with a bunch of sites who are participating with this. OpenLisp, which is a OpenBSD-based implementation of Lisp, is also implementing DDT at this point, and then Verisign is going to deploy a prototype deployment using the existing implementations, but is also working on their own implementation.
So now the OpenLisp is implemented in the BSD kernel. It's so they've tried to keep that fairly efficient. And the Verisign implementation we'll talk a little bit more about in a second.
But deployment and interoperability are going on our beta network today. We have Daryl, we have 100 and something beta sites and in a bunch of different locations around the world. And then we have probably half a dozen different sites that are where the DDT, the regional delegations are made. I have a slide on that in a minute. Nice thing about this is the configuration and the operation is much simpler than alt was. We don't have to deal with any BGP filters, AS number assignments, GRE tunnels, or VRF management. And we also have more flexibility. As Glenn said, we have the concept of instance ID that's part of the EID that allows you to have parallel infrastructure for things like VPNs or for private address deployments where you need to do some sort of encapsulation to get them to interoperate. The current implementation does not include the proposed security extensions that will have a mechanism for doing authentication and signature validation of the actual map request to prevent certain spoofing techniques. Organization and operational status. As I said, we have a beta network going on. Right now, there's a collaboration among Cisco, VeriSign, and a company in Amsterdam called InTouch that is collaborating and working to manage the root zone in the DDT world and operate the infrastructure boxes. Common root, if you go to ddtroot.org, it will actually show you what the boxes are and give you some more information about what's going on now. As I said earlier, this is all running on the LISP pilot network. We did a transition from LISP alt back in March, and we removed the last vestiges, thank goodness, of the alt configuration back in April. And all of us, Daryl and I in particular, breathed a great sigh of relief when that was done. We're looking at a number of different options for how to operate this, how to operationalize this in the future. Should the root be operated and run by a nonprofit, kind of analogously to the way that the root DNS servers are operated, or what sort of model makes sense? We need to focus on transparency. We want this to all be open and people to understand what's going on. And definitely scalability, that's probably the most important issue. And then, of course, efficiency and simplicity, because we want this to be able to be operated without a PhD in routing science. This diagram is just, I don't expect anyone to read it because it's kind of an eye chart, but it basically is there just to show that the existing pilot DDT deployment is distributed. We have a set of root servers up at the top. Those can be operationalized at some point in the future. They're a prototype for that. Then we have, they delegate a chunk of the address space, the prefix 153.16/16, to the LISP pilot network, which then, just for proof of concept, has further split that into regions so that we can get an idea of how easy that is to do and how easy it is to sustain. That's all running today. Again, we have 100 and something sites that are all participating, all using this infrastructure. Glenn's going to talk for a few minutes about the development at VeriSign and what's going on there.
I'm warned I have to talk fast.
Yeah, you have 240.
So we're, right now at VeriSign, we have some gear set up. We're trying to support the open LISP development, and part of the motivation there is, obviously Cisco isn't going to be shipping source code for NXOS out to everybody to show you how they've built LISP, and VeriSign can't release the code that we're working on internally that runs on our infrastructure. So we need somewhere to do this work that's visible. As we continue to produce standards and contribute internet drafts, we need reference code, and Open LISP seems like a good place to put that. Now at VeriSign, we have a pilot program in place that's running a mapping service. We're testing a customer portal to use for provisioning and onboarding folks, very similar to what we do with the registrars now. And this in-house service that I mentioned will be coming online in Q4 of this year, and that'll be deployed on the same infrastructure we use to support the ComNet DNS resolution platforms. And so Vince mentioned a second ago how important scalability is. Our A and J routes in the ComNet resolution platforms have proven scalability. LISP seems like a good fit for those platforms. In our pilot network, we have redundant servers and resolvers at a couple of different data centers with redundant transit and native v4 and v6. Should make some of the folks happy here. I think Martin might be pleased at that. We're running everything on R710s using NXOS right now. The Open LISP DDT capable code is due out in the very next release that they make. It should be in June of this year. We're talking next few weeks. And then, like I said, our map servers and resolvers will be online in Q4 running the native VeriSign code. Now, at the bottom there, we've got some details about the root servers. Like Vince said, that's available from the ddtrootservers.org. And this is just a quick map to remind you guys about what we've got going on in the VeriSign network. You know, if you're concerned about where the Lisp nodes are going to land, we have gear in over 70 places around the globe. Most of our installations have pretty fat pipes and plenty of equipment to handle high query loads. So far, we've got 100% network uptime for more than a decade for ComNet. And that number, 105 million domain names, I think it's up to 120 million now. The point is, it's big. Vince?
I'm just got one slide here just to talk about where Lisp is going. I mean, this is one of the things I want to emphasize is this is not a Cisco project. You know, yes, people that have designed Lisp and worked on it from the beginning have mostly been from Cisco, but we have other people, and it's all being done in an open forum. There's a Lisp working group in the IETF. DDT, actually all of the Lisp documents, the core Lisp documents are already submitted for RFC publication. We're just waiting on some dependencies to be cleared for some non-Lisp documents that they reference. DDT is a draft in the IETF Lisp working group. The version 1 is out there. Version 2 is in progress. It's going to clarify a bunch of things and actually give some more detailed information in the form of a finite state machine or event, decision tree to help implementers actually implement it. Future work, I'm not going to go over that now, but we've kind of covered that already. The ecosystem refers to how the organizational structure will evolve and internet scale deployment. Well, I think we have a pretty good idea how to do that given the model of VeriSign's DNS server deployment. These are the resources. You can look at these later. Some web pages where the first one is general information about Lisp. The second one is, the Cisco implementation information, how to get it. And then the lisp@ietf.org is the IETF Lisp working group, it's open working group. And again, ddtroot.org, that's the Lisp root operators and the status of what we got going there. Questions and comments. Here are some contact information for further information. Lisp support at cisco.com, lisp@verisign.com, and there's actually a mistake in the last one. That's actually lispinterest@puck.nether.net. For some reason, I had a brain freeze when I typed that in, because there's an internal Cisco list with the same name. Definitely welcome input. We definitely welcome more participation, so please contact us if this looks interesting. There's going to be a Lisp presentation tomorrow morning that talks about how Lisp is being deployed today and how it may affect your network. So that's 9:30 tomorrow morning, and that might actually make this a little more real for people. Do we have time for any comments, or am I way over schedule?
We can take maybe one or two and then move on, but we should probably try to make it pretty fast.
So any questions, quick ones? Randy?
Randy Bush, IJ.
Yep.
Your presentation's not up on the web, so I couldn't grep it.
Oh,
But, I kind of was listening for the word security.
Yeah, that was something I knew someone was going to ask that question. There actually are a couple of mentions in the presentation that I glossed over because we were going too fast. The delegation process actually does have a signature mechanism where every delegation from a parent to a child is signed, and that information is propagated through the map referrals. So that information can be verified when you get the delegations and you follow.
What about when you push an update?
There's a separate security mechanism for the ETR to map server registration, and that's actually documented in the map server specification. But that is there. We may be dumb, but we're not crazy.
So in a sense, okay, thank you.
Sure.
In a sense, alt was stick it in BGP.
Yes.
And this is kind of a warped version of stick it in the DNS?
It uses the DNS model of a statically delegated hierarchy, but it uses a totally different platform.
At first I thought it was like a DHT.
No,
But it's not.
It is DNS
it's not
model.
hashed, it's delegated.
But there is, if you look at the DDT specification, there is a whole section that talks about the security model, and we actually have
I was off the security. I was just trying to understand.
sure.
You're structuring and you are choosing a delegation model as opposed to a hash model.
Yes,
And,
because we understand how to make that scale.
okay, thanks.
Sure. Anyone else?
I think that's about it for questions, so.
Okay, thanks. Any other questions, comments? Feel free to contact us on those mailing lists. Thanks.